Hello, and welcome to our program, Astronomy for Everyone. This month's show will be on the topic of the search for life in the solar system. Our guest for this month's show is Dr. Tim Day, a member of the Ford Amateur Astronomy Club and a new member of the Astronomy for Everyone team. Tim, welcome back to the show.
Well, thank you, Don. It's a pleasure to be here.
Now, we're going to talk about the search for life in the solar system. I assume we're not looking for cognitive creatures such as ourselves. So the question is, what kind or type of life are we looking for?
We would be tickled pink to find cognitive creatures, deep thinkers like ourselves or better, which is not hard to imagine. That may exist somewhere else outside our solar system. We don't have any reason to suspect that there's much of that inside the solar system outside of just us on Earth. What we suspect we might find, however, is microbial life, single-cell life, because that is the first form of life and the oldest form of life that has existed on Earth and is most likely to be found on other planets or on moons in other places in our solar system.
So if we're looking for single-cell creatures, what are the techniques or systems that we're going to be using to find this type of life?
There's a couple of ways we can go looking for life. The less expensive methods are Earth-based in that what we do is gather light from the objects we're studying. So we look at the atmospheres of the moons or of Mars, the colors that come in the telescopes, and we put them through spectrometers, and we look, is there evidence of methane, is there evidence of carbon dioxide, photosynthesis, some other lifelike biological gas or molecule that would get us excited. Organic molecules or molecules associated with organic life, yeah. The second way we look for life is we actually go there when it's possible. And certainly planets like Mars and some of the others, Venus and Mercury, and to some extent the gas giants have been visited. And we've literally gone there and looked close up and in many cases crawled around and lifted the rocks up and sniffed the air and done that sort of a thing.
So far, nothing's crawled out from under the rock.
You would have heard about it had it happened, yeah.
All right, well, we're going to take a look, as we said, the search for life in the solar system. We're going to break our solar system, our neighborhood in space, down to two parts. The first part will be the rocky or terrestrial planets, the type that we can stand on like Earth. So let's start there, Tim.
Absolutely. Closest to the sun, of course, is Mercury. When we think of Mercury, think of essentially our moon on steroids. It's a bit bigger, but not lots bigger. It's got a largely metallic interior. It does have a rocky outside, and it's got lots of craters. So if you see the image on the monitor, one of those craters has even got a blue color to it. I believe it's called the Degas crater because of its lovely coloration. It's very close to the sun. Goes around in 88 days. It's tidally locked, which is just a fancy way of saying that the same side faces the sun all the time. So ironically, Mercury has one of the hottest surfaces on one side and one of the coldest surfaces on the backside of any object on the solar system. What it doesn't have is liquid water or even an atmosphere, and not much hope for finding any. Liquid water is very important in our search for life. It's the molecule or the solution scientists think is most likely to harbor life. So that's what we constantly are on the prowl for. We're looking for liquid water, none to be found on Mercury, front or back.
Okay, seems like with Mercury being such a severe case of extremely hot or extremely cold, the chances for life pretty much
pretty thin. Nobody's gotten a lot of energy about spending a lot of time looking under the rocks on Mercury for life.
But then if we go to Venus, the next planet, while it's a little farther away, it's even hotter.
Venus is tremendously hot. When I was growing up, there was a lot of excitement about Venus. No probes had landed there yet. We're talking about the 1960s as I'm going through grade school and learning my science. And Venus was called the sister planet to Earth. It has a similar mass. It has an atmosphere. It's closer to the sun than we are, but not so close as Mercury. What we discovered, especially during the 1970s when the Russians managed to land some probes there, is that Venus has an atmosphere that's much, much denser and thicker than Earth's, and it rains sulfuric acid. More than that, the temperature on the surface of Venus is so hot that it's 700 degrees or 800 degrees, and the probes that the Russians put there would last 10 or 15 minutes, even though they were very, very rugged. They would simply scorch and melt. And if you put a lump of lead on the surface of Venus, it would just turn into a pool of liquid lead. Again, we're looking for liquid life. That's our main goal.
Looking for the water.
Looking for the water. I said liquid life. Looking for liquid water that holds life in it, or can be the solution that life evolves in. And not much hope for it on Venus.
Okay, so let's move to the third rock from the sun.
The third rock from the sun, of course, is our rock, Earth.
Yes.
And it's the planet that is the only place that we know has life at this time. And there is a lot of excitement about planets outside of our solar system that might eventually have life associated with them, but it's very hard to get to them. So we're talking just about the moons and the planets in our solar system today. Life on Earth was always thought to be associated with energy from the sun. So again, when I was growing up, everything I was taught was that it all starts with sunlight, and then it somehow goes through plants, through photosynthesis, and then it's eaten by an animal that's an herbivore, and maybe the herbivore is eaten by a carnivore, but in the end, it's all about sunlight. And in the 1970s, what happened is that we began to discover life on Earth that doesn't depend directly on
such as this image right here.
Sunlight, such as this image here. Deep in our oceans, all over the planet, are these thermal vents. These are like volcanic vents where the magma gets close to the surface of the planet, and black smoke erupts out under huge pressure, black water. It has a lot of hydrogen sulfide in it. It's very poisonous, and it comes out at very, very high temperatures. To our amazement, there is life. Bacteria thrives on converting the hydrogen sulfide into chemicals that can be eaten by tube worms, and then the tube worms have fish and crabs associated with them, and you have this whole ecosystem that grows very rapidly around these hot seeps or these hot vents around our planet. And the bacteria is very, very old bacteria. It dates back to the beginning of life on our planet, and it's very similar to each sort of vent all over the planet, the life around each one.
So seeing this type of life, as we were just talking about, it's possible going to other worlds, say some of these moons of the gas giant?
That's our hope.
If we find those same type of or similar circumstances.
We're looking for liquid water, and if we can find liquid water and we can find a similar circumstance, then we may well find life. There's a second source of deep water life that is independent of sunlight that has sunlight that's recently found, and these are methane seeps. These are cold areas on the ocean floor where methane, which is usually a gas that would burn on your stove, is actually a waxy substance. And again, it's kind of poisonous, sort of toxic, but yet there are bacteria that manage to convert it into a usable chemical energy, and then there are worms that live on the bacteria there, and there's a whole life system that, once again, is exciting because it's independent of the sun directly. It's purely chemotrophic.
All right, well, we've got one more planet to cover in our inner part of the solar system, and that's the red planet.
The red planet, the fourth one from the sun, has been the planet that has always been the most exciting, and we certainly sent most of our probes and spent most of our time looking there for life. Mars is farther away from the sun than Earth is. It has an atmosphere, but the atmosphere is very, very thin compared to ours, much thinner than even at the top of Mount Everest. It's almost all carbon dioxide, and it doesn't have very much water vapor with it. Again, we're looking for liquid water. That's always the goal.
Okay, and I know we found some frozen water ice underneath the soil. We've also noticed that there is frozen water ice at the poles, so perhaps this will be part of the thing that'll help us possibly find something.
We have not given up hope. There are rovers that are actively crawling all over the Martian surface now, turning over rocks, sniffing the air, doing chemistry experiments, and it's entirely possible that microbial life may yet be discovered on Mars. We've been looking for a good 30, 40 years. We're not there yet, but we haven't ruled it out.
All right, well, this sounds like it's been a really great and interesting discussion. I'm quite fascinated by this, actually. But before we move out to the outer solar system, we're going to take a quick break. If you have a question for us, please send us an email. You can see the email down there at the bottom of your screen. And coming up next is Stephen Whitty with Term of the Month. And after that, we'll be back with Dr. Tim with more about the search for life in the solar system.
The term of the month for April 2015 is gravity. Gravity is one of the 4 fundamental forces. It causes objects to attract each other. It gives objects weight. All things fall towards each other due to gravity. Isaac Newton published his theory of gravity in his Principia in 1687, as we heard last month. In it, he included a simple formula. F is the force between the 2 objects. M1 and M2 are the masses of each of the objects, so one might be heavier than the other. R is the distance between the objects, and you can see that it's squared. The force falls off with the square of the distance. It goes down quickly. And then G, the big G, is a gravity constant. You can kind of ignore it. It's always the same. Now, this is a relatively easy formula to use, but even so, if you want to predict exactly where a comet is going, which is what Haley wanted to do in last month's episode, you need calculus with this formula to actually solve it. And although a computer isn't absolutely required, it's a lot of numeric crunching that you have to do, and it's very difficult to do without a computer. In 1915, Albert Einstein published his general relativity. And general relativity modified Newton's gravity to include the effects of very high gravity areas, like near a star, or at very high speed, like near the speed of light. In this image, we show the Earth creating a gravity field, and this is kind of a representation of what the gravity field might look like. And we have a satellite on the left there sort of orbiting the Earth. This was gravity B, in fact, which was measuring the gravity field. So we're just looking at warped space-time. In general relativity, the math is much harder. Instead of some simple algebra, you have the field equations for general relativity include 10 simultaneous, nonlinear differential equations. You need, 4th or 5th or 6th semester calculus to have any hope of it. And you absolutely need a computer to come up with the solutions to these equations, which then allow you to predict the path of some object through some gravity field. General relativity is probably not the last word on gravity. General relativity and quantum mechanics are known to be incompatible, and so we need something that will do both in order to predict either a black hole or the beginning of the universe. And that's gravity. Term of the month for April 2015.
Thanks, Stephen, and welcome back to our program. We're talking with Dr. Tim Day. He is our guest this month, and the topic, once again, is the search for life in the solar system. Now, Tim, we were talking in the first part about the inner planets, the rocky planets. Now we're going to turn our attention to the gas giant planets. And because they have no solid surface, just being gas, we're going to concentrate more on some of the moons of those planets?
We will. The gas giants are 4, like the terrestrial rocky planets. We've got the biggest of them all, Jupiter, which is the next one out from Mars, and it's got a fabulously colorful atmosphere. But even though we have thrown a probe down into it and studied it for many, many years, there's not much thought of there being liquid life in that atmosphere, and certainly deeper into the planet's core. Again, no thought of liquid water, and therefore no life in that water. But the moons The moons of Jupiter and of Saturn are far more exciting, and this is relatively new information for us.
All right. Is there one for Jupiter that catches your attention?
There is. The most exciting moon around Jupiter in terms of looking for liquid water and thus possibly life is Europa. So there are 4 huge moons that orbit Jupiter, from the innermost Io, which is the smallest, and it has active volcanoes on it. And we see magma erupting into space in huge geysers. It's just a remarkable little rocky moon. Then the next one out is Europa. And that is a moon that is not at all volcanic unless the volcanoes are contained underneath a shell of ice that encases the planet.
Interesting. And here's an image of it
Here's
right here.
the image of it. And the interesting thing about Europa is that the surface is relatively fresh. We see scars and long lines.
Yeah, there's one impact crater right there.
A couple of impact craters, but things like moons, like our own moon, are typically covered, or Mars or Mercury, with hundreds and thousands of craters that show, the fact that impacts happen in our solar system all the time. Europa is smooth, and this suggests to scientists that water is continuously seeping out from underneath ice and covering the surface, hiding the
flowing through the cracks and
flowing through the
refreshing
cracks and refreshing the surface. And we even have pictures of geysers, water geysers, coming out. So here's a picture of Jupiter, and to the right is the moon Europa. And Europa at the top, you can see, has a little white spot, and that actually is a water ice geyser. So here's a slide. It's a drawing. This is not an actual image of what we think the ice giants like Europa may look like. An outer layer of ice, and then a liquid salty ocean that may be hundreds of kilometers deep, and there may well be volcanoes and or warmth that is generated by frictional pulling, compressing, and sort of a taffy-like effect on the planets that keeps the moons,
something
that
like
keeps
the
them
thermal
warm.
vents that we saw here on Earth.
Exactly like the thermal vents we see here on Earth.
Okay.
So we've got the elements potentially to make us very excited in the search for life on these icy moons. We've got liquid water that is certainly there. We see it. We see ice plates where the water would meet space, and it keeps the water from boiling off. It protects it from from space. We see that the ice plates are moving, that they collide with each other, that they're refreshed. And we know that there are almost certainly sources of energy underneath that salty water that could be sources for bacterial life.
Interesting.
It is. It's a very exciting time. Nobody ever suspected that we would be looking at moons of gas giants in our search for microbial life in our own solar system. It may turn out that gas giants with moons similar to Europa or Callisto or Ganymede or some of the other moons that are in orbit around Saturn, those are actually moons that may typically harbor life as we start to look at systems outside of our own solar system. Earth may be a very unusual planet in that it has salty waters, oceans, that don't have a complete covering of ice all the way around them, that there's liquid water that's protected by an atmosphere dense enough to keep it from boiling away into space without needing an ice cap.
Speaking of the planets, if we move out to Saturn and its moon Titan, the only moon in the solar system with an atmosphere.
It is the only moon with an atmosphere, and Titan is a very exciting place. We've actually landed there in the not too distant past.
About the last 10 years, I think.
It's been very recent. And the Cassini probe, which was sent there, put a lander down on the surface of Titan. It had parachutes, used the atmosphere to go through, and it actually landed on the surface of Titan. And Titan, it turns out, is pretty cold. I mean, it is around Saturn, which is far from the sun.
Yes.
But it does have an atmosphere. It has liquid oceans. The oceans are made of methane and other hydrocarbons. And it actually has weather. So it rains these hydrocarbons.
Methane
and ethane and propane and butane and all of these hydrocarbon type molecules that can be liquid at these cold temperatures.
Typically, what, 250, 300 degrees below zero?
Yeah, and that's very cold, too cold for liquid water. So we're not very excited about the possibility of finding liquid water on Titan, even though it has an atmosphere and it does have the presence of weather and liquid oceans. It's just that the oceans are made out of hydrocarbons, and there's not a lot of reason to suspect hydrocarbons support life. We've been very surprised before in our search for life, even on our own planet. So never say never.
That's right. That's right. You never know.
Yeah.
The last two planets in the solar system, Uranus and Neptune, what are the possibilities there on some of their?
These are gas giants that are similar to Jupiter and Saturn. They're a little bit smaller. Here's a photo of Uranus. That's actually two pictures of it. And it has a gas atmosphere much like the other Jovian planets, and it's interesting because you can see here it actually rolls around on its side. A long time ago in our solar system's history, something must have hit it and knocked it over, and now it sort of rolls around with its equatorial belt facing down. It does have some big moons. We don't have any reason to think that there's much liquid water on those moons. And they're very cold moons. So while we're learning more about Uranus, there's not much reason to think that there's the chance to find life there compared to, say, the moons around Jupiter or around Saturn.
How about the big moon of Neptune, Triton?
Triton's moon, Neptune's big moon, is a place that certainly has an atmosphere, but and a rocky core. It is one of the coldest places in our entire solar system. Mm-hmm. So temperatures there are just a few degrees above absolute zero, no liquid water, no liquid anything to speak of, not much chance for life there as we understand life as it operates now.
And how about Pluto and the other dwarf planets, Kuiper Belt objects?
Yes, the smallest item. So here's an artist's drawing, the graphic of Pluto, and it has a large moon called Charon. And Pluto is suspected to have a bit of an atmosphere that probably freezes when it gets far away from the sun in its orbit, and then becomes an atmosphere again when it warms up. It has a couple of smaller moons, but again, no reason to think that there's liquid water, and so no reason to get very excited about the possibility of life on these types of planets. The Sedna is another moon that is even farther out than Pluto, or dwarf planet.
Eris, Haumea.
Yeah, like that. But they're small, much smaller than our own moon, and bitterly cold. So again, not much reason to be thinking life on those icy bodies.
What about future work, looking out 20, 30 years?
That's the work for the next generation. That's the exciting stuff. Life is precious. Anytime we have a chance to find it on our own planet or somewhere else, what we want to be doing is taking that opportunity. So I want the next generation of scientists coming up to think in terms of how are we going to land on Europa? How are we going to send something with a nuclear, core and has the ability to drill down through the ice cap and send a submarine in and actually look for life? Are we going to send less expensive probes that fly through the geysers and sample the water that's spurting out? There's all sorts of possibilities. That's the work for the up and coming generation of scientists. They should be excited because there's a very good chance that they will find something that will change our understanding of life in the solar system.
Thank you, Tim. I want to thank you very much for being here with us today to share this search for life in the solar system. We would like you to visit our club website if you would like some additional information. Our club website is down there at the bottom of your screen. And hopefully you've enjoyed our topic for today. Coming up next is our own Steve Whitty with What's Up in Our Night Sky. So don't go away.
What's up in the night sky for February 2016? We're still getting farther from the winter solstice, so the days are getting longer. So here in Michigan, Sunrise at the beginning of the month is at 7:45, and sunset is at 5:45 p.m. By the end of the month, sunrise is 10 minutes after 7, so it's 40 minutes earlier. And sunset is at 6:22, so it's about 40 minutes later, so the days are getting longer. The moon phases in February this year are very strange. New moon is on the 8th, first quarter is on the 15th, the full moon is on February 22nd, but the third quarter actually lands in March 1st. Well, January 31st and March 1st are phases, and so February this year gets gypped out of a phase. Very, very strange. All of the planets this month are in the morning. Here on February 7th, we have on the left, we have the moon, which is a day before new moon, so actually earlier than the 7th is better for actually seeing the moon, and it'll be somewhere along the string of planets that you'll see here. Mercury is next up, and I chose the 7th because Mercury is at greatest elongation. It's farthest from the sun, so it's highest in the sky. It'll be the easiest to see. And here on the 7th, I recommend 6:50 a.m., at least in Michigan. So if you started out at like 6:30, then you should be able to see things almost no matter where you are. And then Venus is next. Venus rises around 6 in the morning. Saturn rises maybe 4 in the morning. Mars rises maybe 1:30 in the morning. And Jupiter rises around 9 at night. Jupiter is about to have opposition. That's March 8th. So it'll be up all night in March. Mars is going to have its opposition May 22nd, so it's going to be the biggest it'll be for quite a while in the sky then. So that ought to be awesome. And Saturn has an opposition June 3rd, so it will be gorgeous, certainly. We do have kind of an interesting thing coming up in May, a transit of Mercury. This transit of Mercury will be visible in Northwest Asia, Europe, North America, and most of the Pacific. But it's hard to see because it goes across the sun. The transit goes across the sun, so you need a telescope with a solar filter. There are other ways to see it. Go to an astronomy club that's having an outing, they'll set you up properly, or get yourself the right equipment, but you also need the times, local times, and so on. And then we have something from the news, Planet 9. Planet 9 was announced. Planet 9 really hasn't been discovered yet, but they talked about how we need something that would cause these other objects that we've discovered to have the orbits that they have. Hasn't been discovered yet. We're hoping for it pretty soon. And that's what's up in the night sky for February 2016. Keep looking up. It's the greatest show straight over your head.